Okay, so you know how it is, right? You're trying to stay on top of what's new in tech, but you've got this, mountain of articles, research papers. It can be totally overwhelming.
Yeah, definitely. Information overload is a real thing.
For sure. So that's where we come in. Think of this as, your shortcut, a cheat sheet, a way to cut through the noise and get to the really juicy stuff. We do the deep dive, the heavy lifting into all that material you shared, pull out the key insights, and hopefully make it fun along the way.
Absolutely. We've done the hard work, sifting through all the details, connecting the dots, all that, so you don't have to. The goal is to give you a clear, concise understanding of the topic at hand.
And today's topic is a particularly cool one. We're talking about how AI, artificial intelligence, is not just being used in the design of FPGAs, field programmable gate arrays, but is actually making them significantly better.
Yeah, it's a really fascinating area, and we've been diving into articles, research papers, all sorts of stuff, focusing especially on this document on AI improving FPGA design.
Right. So before we get too far, maybe just as a super quick explanation for anyone who's not a hardware geek, what exactly are these FPGAs?
Sure thing. Think of them as incredibly flexible integrated circuits, kind of like a blank slate for hardware. Unlike your typical CPU or GPU, which have a fixed architecture, an FPGA can be reconfigured after it's been manufactured to do specific tasks.
So it's super customizable.
Exactly. It's almost like having hardware that you can digitally rewire on the fly.
Okay, I'm starting to get it. So that reconfigurability, that's got to be a huge advantage, right?
Yeah.
But I imagine that level of flexibility also creates some challenges.
Oh, for sure. Designing and optimizing these things, that's not a walk in the park. I can tell you that.
Right. So how are people traditionally going about this?
Well, the challenge is that optimizing an FPGA for, say, speed, power efficiency, or size, it's really tough using the old methods. I mean, these chips, they've got tons of configurable elements, all these crazy ways they can be interconnected. It's just like a massively complex optimization problem.
Right. So traditionally, you have engineers using these electronic design automation tools, EDA tools, which are basically software to design the hardware. But you're saying those tools are hitting their limits.
Yeah, kind of. They often work on a set of predefined rules, which can be limiting. They might not always find the absolute best solution for a given task, like the best way to configure the FPGA to do a specific thing, it might not be obvious based on just those rules.
Got it. So that's where AI comes in.
Exactly. AI offers a completely different way to approach this complexity. Instead of being stuck with pre-programmed rules, AI algorithms, they can learn from massive amounts of data, seeing patterns and figuring out ways to design and use FPGAs that are way more efficient and innovative.
Okay, AI to the rescue. But what does that actually look like? What types of AI are we talking about here?
Well, the research we've been looking at highlights a few key players. There's machine learning, deep learning, and reinforcement learning. They each bring something unique to the table.
And how are these different AI approaches being used in the actual FPGA design process?
Yeah. Well, think about the entire journey of an FPGA design. You start with an idea for what you want it to do, the functionality, right? Then you got to translate that into a detailed hardware description that's high-level synthesis. Then you got to figure out where all the components go on the actual chip, how they're all wired up. That's the place and route stage. And AI is being used across this whole spectrum.
So instead of engineers manually tweaking things for hours and hours, relying on those traditional EDA tools, AI can come in and automate and optimize those really critical steps.
Yeah, precisely. It's like having an extra super smart team member who never gets tired and can see things humans might miss.
Right. And the benefits, they're not just limited to the initial design phase, are they?
No, not at all. AI is also being used to make sure those applications run as smoothly as possible once they're actually on the FPGA. It can manage resources intelligently, predict bottlenecks, and even adapt on the fly to changes in the workload.
So the AI is constantly learning and improving, right? From previous designs, from simulations, and that kind of thing.
Exactly. It's constantly learning and potentially finding solutions that human engineers might not have even thought of. Which brings us to some really interesting real-world examples of how all this is actually playing out.
Let's hear it.
Well, one really fascinating case is Microsoft's work with Project Catapult and then Brainwave.
Okay, Microsoft. So they're obviously a giant in tech with huge data centers running things like Bing search and all their AI stuff. And those demands are only going to grow, right?
Oh, yeah, for sure. And with Moore's law slowing down, the traditional rate of improvement in processor power, they had to get creative. FPGAs offered this really sweet spot closer to the performance of custom-designed ASICs, but with more flexibility than traditional CPUs. So they launched Project Catapult to basically supercharge Bing searches using Intel FPGAs alongside their Xeon processors.
And how did that work out for them?
I'd say pretty well. They did a massive deployment, over 1,600 servers, and saw a 95% boost in search query throughput, basically, how many searches they could handle. And get this, with only a 10% increase in power consumption.
Wow, that's a huge efficiency gain.
It is. It's like they effectively doubled their search capacity with barely any extra energy.
And it sounds like AI played a key role in squeezing that performance out of the FPGAs.
Yeah, a lot of the magic probably came from AI optimizing the FPGA's interconnect fabric, minimizing the delays for those specific search algorithms.
So supercharging web search. What's next?
Well, then they moved on to Project Brainwave.
Which is all about AI, right?
Yep. Shifting focus to speeding up all their AI workloads in the data centers. And while they don't shout about the exact numbers, the fact they're using FPGAs for this tells you everything you need to know.
Right. They would be deploying them at that scale if they weren't getting serious results. So from search to AI, all on FPGAs, that adaptability is pretty impressive.
It really is. Speaking of making technology more accessible, let's talk about what Amazon Web Services, AWS, is doing with their EC2 F1 instances.
Right, AWS. So they're making it possible for anyone to get their hands on this powerful tech, even if they don't have the resources to buy and manage it all themselves.
Exactly. It's like democratizing access to FPGAs. Anyone can basically rent access to Xilinx UltraScale plus FPGAs in the cloud. No huge upfront costs, no headaches of managing hardware.
So it's FPGA power on demand. And I imagine the use cases are pretty diverse.
Oh, absolutely. It's being used all over the place, especially with the rise of AI. You've got machine learning inference, using those trained AI models to make real-time predictions. FPGAs can often handle those calculations much faster than CPUs. Then there's big data analytics, crunching massive data sets to find insights. Even fields like genomics, where the computational demands are huge. FPGAs on F1 are providing big speedups.
And what about video processing? Encoding, decoding, that sort of thing.
Oh, yeah, that too. It's a perfect fit. I mean, there's this company, Intel, they've developed tools that run on F1 instances, and they can speed up those common machine learning algorithms used in Apache Spark ML, things like logistic regression and ALS. They're seeing speedups of 3 to 20 times.
That's insane, just by harnessing the power of the FPGA.
It is. And here's a really cool twist. FPGAs on those F1 instances are even being used to accelerate the design process of other chips, including, get this, other FPGAs.
Wait, they're using FPGAs to design FPGAs? That's like super meta.
I know, right? This company, Silver Lining EDA, they have this tool called Verifier. They use the parallel processing power of FPGAs on F1 to dramatically speed up chip verification, which, as you know, is a crucial part of the design process.
Right, you have to make sure the chip actually does what it's supposed to do before you start making millions of them.
Exactly. It's usually a super time-consuming process, but they're reporting speedups of up to 1 million times compared to traditional software-based verification methods.
1 million times. That's not just an improvement, that's a complete game changer.
Totally. It's a huge bottleneck in hardware development, but they're addressing it head-on with FPGAs, which means faster development, better chips, you name it.
So we've got big companies using AI and FPGAs to boost their own infrastructure and help others do the same.
What about the world of scientific research? I know some fields, like particle physics, they generate just absolutely mind-boggling amounts of data.
Oh yeah, definitely. Like the Large Hadron Collider at CERN or the Beltasec experiment in Japan, those are just pumping out data like you wouldn't believe. And they need to process it all almost instantly to find those scientifically interesting events, the needle in the haystack.
And FPGAs are up to the task.
Oh, they're ideal for this. Massive parallel processing, ultra-low latency, meaning there's barely any delay in processing. Traditional software just can't keep up with that kind of data fire hose.
So at CERN, they're using deep learning on FPGAs to track those particles, right?
Right. It's called charged particle tracking, and it's crucial for reconstructing the paths of all the particles created in those high-energy collisions. And deep learning, it can learn complex patterns from that raw sensor data, leading to much better data acquisition, which is key for making new discoveries. So AI running on FPGAs, helping us make sense of the subatomic world.
It is. And Second, they've actually integrated machine learning on FPGAs into their systems, doing things like real-time triggering and data reduction.
So instead of getting overwhelmed by all the data, they can focus on what's really important.
Yeah. They've got this neural network, the level 1Z trigger, which filters the data and cuts the rate down from 130 kilohertz to 30 kilohertz.
Huge reduction.
Yeah.
And they have other tricks up their sleeve too, right?
Oh, yeah. They've got this neural Z-vertex trigger, uses a multi-layer perceptron, and it can estimate the 3D origin of particle tracks super fast in just 300 nanoseconds, and it runs continuously. And then they have this NeuroBayes algorithm also on FPGAs, which helps with particle identification by reducing noise by 90% while keeping the important signals.
That's amazing. AI and FPGAs are making a real impact in particle physics, a field where every tiny bit of data is precious. Now, what about some of the more experimental areas of research?
Well, there's a ton of really cool stuff happening with neural compression inference accelerators on FPGAs.
Oh, that's a mouthful. Can you break that down a bit?
Sure. It's basically about running machine learning efficiently on a wider range of devices, not just those power-hungry GPUs or TPUs. FPGAs are great for this because they can balance performance and energy efficiency. And the key here is compressing those complex neural networks, making them smaller so they can fit and run well on an FPGA.
So how do you compress a neural network?
There are a few different techniques. You can prune away less important connections in the network. You can quantize the weights and activations, meaning you use less precise numbers to represent them. And you can also use weight sharing, where multiple connections use the same weight value.
So you basically make the model leaner and meaner so it can run on the FPGA without losing too much accuracy.
Exactly. And researchers are developing specialized hardware for FPGAs too, like the NCIA, the Neural Compression Inference Accelerator. It's designed to handle the types of calculations you see in these compressed networks really efficiently. And there's also this cool tool, HLS4LMUL, that helps translate those high-level machine learning models into hardware implementations for FPGAs.
So better performance, lower power consumption, that's huge, especially for things like edge computing, where you need to be mindful of battery life.
Right. Speaking of edge computing, let's talk about split learning on FPGA sensors.
Split learning. Okay, that's a new one.
It's all about doing distributed machine learning, but in a way that protects privacy. So imagine you've got all these sensors, like in a hospital or a secure facility, each equipped with an FPGA. With split learning, the FPGA on each sensor does the initial processing right there on the spot and only sends intermediate data, not the raw stuff, to a central server.
So the sensitive data stays put, never leaves the device.
Yep. That's super important in places like healthcare, where privacy is paramount. You can have all these devices learning collaboratively without ever sharing that raw, potentially sensitive data.
Really clever solution. So we've covered a lot of ground, seeing how these different AI approaches are shaking things up in the world of FPGAs. Can we step back and recap the main AI players here?
Definitely. So we've got machine learning in a general sense. It's great at finding patterns in data and making predictions. In FPGA design, it can help optimize resource allocation, improve those place and route algorithms, and even predict how well a design will perform.
So using past experience to make better design decisions. Got it. What about deep learning?
Deep learning, that's your heavy hitter for super complex problems. You know, those massive neural networks, they're perfect for exploring the huge number of possibilities in modern FPGAs. Deep learning can even help automate design generation, literally creating parts of the FPGA design from scratch.
That's wild. So it's not just optimizing existing designs, it's coming up with brand new ones.
Exactly. It can find solutions no human would have thought of. And then there's reinforcement learning.
Reinforcement learning, remind me how that one works again.
Think of it like training a dog. You give it rewards when it does something good, punishments when it messes up. It learns through trial and error. With FPGAs, you can use reinforcement learning to fine-tune design parameters based on how well they perform. It's even got the potential to let FPGAs reconfigure themselves on the fly, adapting to whatever you throw at them.
That's pretty futuristic. A self-optimizing chip. Okay, but all this AI integration, it can't be all smooth sailing, right? What are some of the challenges?
Oh, for sure. One big one is data, or rather, the lack of it. To train these AI models properly, you need lots of high-quality data designs, performance stats, the whole shebang. But a lot of that is locked up in companies, is proprietary, and even when you can get it, there are no real standards, so it can be a mess to use.
So it's like trying to bake a cake without the right ingredients or a recipe.
Yeah, pretty much. And then there's the challenge of integrating all these fancy new AI tools into the existing design workflows. Engineers are used to their commercial EDA tools, and throwing AI into the mix, that can be disruptive. You've got compatibility issues, you need to figure out how to connect the tools, there's a learning curve.
So it's not as simple as just downloading an AI plugin and hitting go.
Nope. There's work to be done to make these AI tools play nicely with the tools that are already out there. Open source frameworks, standardized APIs, good documentation, training, that's all going to be key. And of course, there's the elephant in the room, the FPGA itself. It's a finite resource, you can only fit so much on there.
We're at the hardware limitations.
Exactly. So techniques like model compression, that's essential. And companies are working on specialized hardware architectures for FPGAs, making them more AI-friendly. You've got platforms like AMD Vitis AI and Intel OpenVINO that are helping developers get AI models running efficiently on FPGAs.
So it's a two-pronged approach. Make the software, the models, smaller and more efficient, and make the hardware, the FPGAs, better at handling AI. Big picture. What's the overall impact of all this? Is AI really changing the game for FPGAs?
I'd say absolutely. It's making the whole development process so much faster, design, optimization, verification, everything. And the performance gains are huge. We're talking higher frequencies, lower power consumption, better use of the chip's resources.
It's like AI is pushing the boundaries of what's possible with hardware.
For sure. And it's just the beginning. We're seeing AI being used for even higher level design tasks, like automatically generating hardware code. And it's helping create smarter verification and debugging tools.
Catching those errors before they become big problems.
Exactly. And then there's the whole world of specialized AI hardware on FPGAs, especially for edge computing. That's exploding right now. And adaptive reconfigurable systems where the FPGA can actually change its functionality on the fly based on what the AI decides, that's coming too.
So this marriage of AI and FPGAs, that's only going to get stronger, leading to even more powerful and versatile computing platforms.
Yeah.
But there's still lots of work to do, right?
Oh, yeah, tons. We need better AI models, ones that are specifically designed for the quirks of FPGAs. We need better open source tools, better ways to integrate AI into the design process, and exploring new AI techniques like neuromorphic computing or even quantum stuff, that could be huge. And of course, with all this AI in the mix, we need to make sure everything is secure and trustworthy.
So to sum up, it's pretty clear. AI is changing the FPGA landscape. It's not just tweaks and improvements. It's a fundamental shift. Faster development, better performance, and new applications we haven't even dreamed of yet.
Totally. And those numbers we talked about earlier, those are the proof. Microsoft's Project Catapult, 95% throughput increase. That crazy million times speed up in chip verification on Amazon F1 instances. Bell II's trigger rate reduction, handling all that particle physics data. Those are huge leaps forward.
So to our listeners, think about this. How do you see this whole AI FPGA thing playing out in the areas you're interested in? What no possibilities do you see on the horizon? It's a wild ride, and it's just getting started.
Couldn't agree more. It's a fascinating field, and it's going to be incredible to see what happens next. If you're interested in this stuff, keep digging, keep exploring. It's well worth your time.